Welcome, grade 11s. You're back. It's 5 p.m. here on this lovely Tuesday, and we're doing physical sciences. It's me, Megs, and I'm with my compadre over here, John, as my compadre with physical sciences. So what are we doing today?
Megan, it's great to be with you today. Guys, today we're carrying on with Newton's laws. Last week we did Newton's laws of motion, and we focused on Newton's second law. Today we're taking it a step further. We're going out into space.
Weightless.
We're talking about Newton's universal law of gravitation. Now, that's really an interesting topic.
Very. I wish.
You know, gravity sucks. No, it doesn't really. But some people really get upset with those gravitational problems. We're here to solve all of them. So get on the page. Megan, how can they do that?
It's so easy. All you have to do is go to Facebook, facebook.com/learn extra, and you just click on that. Please tell your friends, share with them, tell them to like our page. Let's get the community going here, Mindsetters. And I think we should also tell you about Twitter. That's @learnextra.
Okay, great one. Now, guys, we're going to start off today with a challenge question. And this is a question that has baffled people for many years. But let's go and have a look at it. We're going all the way back to Roman times. And before we get into the explanation, let's have a look at the challenge question. Now, the challenge question is on the website.
Yes.
We're going to have a look at it in a minute. We're going to have a look at it. But I want to just get through the challenge question, make sure you understand it. So the first thing you've got to recognize, it's a statement that it's saying to us, a falling object that falls towards the earth because the force exerted by the earth on the object is greater than the force exerted by the object on the earth. So that's a statement that somebody's made. What you've got to decide is the statement true or false? And then very importantly, you've got to explain it. So not good enough just saying true, false. Huh?
True, false, F.
Flip a coin, maybe,
Don't know.
maybe, I don't know. No, that's not an option. Choose one and then explain why you say it's right or wrong, why it's true or false. Okay.
Okay. Well,
Megan,
I just
what
want
else
to
is
tell
going
them,
on?
okay, of course, we can't forget about our competitions. Obviously, we have the Test Yourself competition. Mindsetters, that is important because you could win really cool prizes, proudly sponsored by Vodacom, and I would get entering if I were you. But I have to announce the winner for this grade 11 show, and congratulations.
That's from yesterday's show.
From yesterday, yeah.
Guys that entered for the math show yesterday, some multiple choice questions, the links are all on the page, and if you can't download the notes, we'll be posting the questions for this show during the ad break. So stay on the page, watch carefully.
Exactly. So the winner for yesterday's show,
Drum roll.
is Bongiwe Nkosi. So congratulations to you. You have won yourself 110 Rand Vodacom airtime.
That's really great. Now, in case some of you have been hearing that name and you've heard Progress's name and Bongiwe, the reason they've done it is they got the most answers correct in the shortest period of time. So guys, don't wait for tonight's 10 o'clock deadline and submit it 2 minutes to 10. No, get your answers in as soon as possible. Because I'll be checking those answers first thing tomorrow
John
morning.
checks all the answers.
And we'll check and see exactly who's got them right.
And don't forget to go onto our page at learn.mindset.co.za to find out all the show notes and all the videos and all the things you need to know about the Learn Extra live shows.
Excellent. Now, there's one other thing that I want to just show you, and this is really important. We're getting really excited about this. We've started, and I want to show it to you on Facebook. I'm going to go to the board now just to show it to you. We've started a campaign about walking together. Guys, we want to be friends. We want to make this community stronger. We want to go all the way. We're here to go with you for the year. And we're starting off with a great second type of competition, which is about Tommy Tackies. Now, my board seems to have frozen. Tommy Tackies have given us some prizes, and we've posted this little picture. Let's see if I can highlight it. See if we can get a color going there. It doesn't look like it's doing it.
Fighting.
But what you've got is a whole lot of people that have captioned that photo. And what we want you to do, go and have a look on the page, find it. It'll be up at the top of the page at the end of the shows. see the comments, like the one that you like best, the comment you like best. If you don't like any of them, put your own caption. Get your friends to like your caption. The winners of this competition, most likes by Friday, okay? First 3 top likes, they're going to get a pair of Tommy Tackies, your own size, direct from Tommy Tackies. Thank you to Tommy Tackies. Okay, isn't that cool?
That's awesome.
So
and by the way, we're also going to be getting Tommy Tackies,
Yeah.
proud sponsors. Heck yes. So is your board frozen?
No, that part we're going
All
on.
good.
Let's move on.
Let's get going.
Okay, so guys, we've done the challenge question, we've done the competitions, now let's get into the science. The first thing we want to talk about is what's this law called Newton's law of gravitation all about? Universal law of gravitation. Now, you must have heard the story about Newton sitting under a tree and he suddenly sees an apple falling. Now, how did he explain it? What did he say was happening? Well, there's a whole lot of anecdotal stories about that you can read in lots of different textbooks. But really, the story that Newton was doing, looking under the tree, was he was observing the stars. He was observing the moon, and he wanted to understand why they were in a fixed orbit. Why it was that he looked at and he saw the stars always in the same sort of pattern. Yes, they rotated in terms of the time of season, but he was trying to explain what was going on. And then he saw the falling apple at the same time, and he suddenly realized that there was a force between objects that have mass. He recognized the sun has mass, recognized the moon has mass, recognized the earth has mass, the stars have mass, the planets have mass, and because they have mass, there must be this force pulling on them. So that's why he came up with this idea, which we call the law of universal gravitation. So here it goes. We want to break it down and explain it step by step. He said, the force of attraction between 2 objects in the universe, any 2 objects, they must have mass. Okay? They must have mass. And what we say is they're directly proportional to the product of their masses and inversely proportional to the square of the distances between their centers. Wow, that's a huge mouthful. I need to take it one step at a time. And I want to explain to you each of those important terms and revise with you. I know you've been dealing with relationships right from probably grade 8 when we started some natural sciences in high school. But let's just draw a picture so we can see. Let's talk about this object as having a mass, m1, this object having a mass, m2. The first statement is the force of attraction between these 2 is directly proportional to the product of the masses, m1 times m2. Product means multiply. What does directly proportional mean? Think about it for a minute. Hope you've got it. That's right. When you increase 1 by a certain factor, then the dependent variable will increase by the same factor. So let's just take it like this. If we start with mass 1 and then we double the mass of m1, what's the force going to do? Well, it's going to double as well. So if we increase this mass, make it go up by a factor of 2, then the force will increase by a factor of 2. Now, how about this? If we increase the force of the mass of m1 and the mass of m2, so now we've multiplied the one side by 2 times 2, which is 4, then we must multiply the other side by another 2, so it's gone up by a factor of 4. Guys, you've got to be very careful with this. You've got to know it. Directly proportional means if I decrease the 1, halve the mass. So they often say halve the mass. That means I multiply by a half. Then I must multiply by a half on that side. What I do to the one side, I must do to the other. And it's a proportionality factor. It doesn't mean that I can add or subtract. No, it's multiply either by a whole number or multiply by a fraction. Yes, we can divide. We know that's the same as multiply by a fraction. Okay, so there's the directly proportional. There's one other thing that you mustn't forget when we're dealing with directly proportional. And this term is very, very important because we'll come across it in many different places, in this year and in grade 12. So you need to know this. If we were to plot a graph, okay, and we plotted a graph of factors that are directly proportional to each other. In this case, I'm going to do the product of the masses, m1 times m2, and I'm going to say force is on that set of axes. Now, in this example, and in fact in any example, the things that go on the horizontal axis, they're known as the independent variables. And this one on the vertical axis is known as the dependent variable. Now, when the things are directly proportional, then we know, and I want to get a nice straight line to represent it, then we know passing through the origin, there will be a straight line. Okay? So it can't be just any old place that it starts from. It's got to go from the origin. So let me make sure that it is at the origin. The origin is this point of 0, 0. So it must go through the point 0, 0. Okay? It's got to go through that point. It's got to start at the origin, and it's a straight line. It has a constant gradient. It's directly proportional. Now, this you should be able to apply to Newton's second law. Remember last week we said the acceleration is directly proportional to the net force. So if you've been plotting graphs for Newton's second law as a practical, then you'll know that you've got directly proportional. This is another example of directly proportional. Okay, let's go on to the next part of the law. So we've covered the first part. We've covered up to there. But it then carries on and says, and inversely proportional to the square of the distances between their centers. Okay, now let's break that down just to make sure that we've got it. When we're talking about Newton's universal law of gravitation, we're talking about masses, and we've illustrated them as spheres, and we say they both have centers. And what we're interested in is the distance from that point, from M1 center to M2 center. So that distance there, all the way through. Now, this would be the radius of M1. This would be the radius of M2. And what we're wanting to get is the whole distance, not just the radius, but just remember that it's from that point all the way to that point, and it's from the centers. We call that distance, let's call it an R. I'll even call it a big R. What we're going to say is that the force is inversely proportional to R squared. So if we're taking that whole distance as R, and we're not just talking about R, but R squared. Now guys, that's quite a factor, that we're having to square R. And this is the place that a lot of people make mistakes. I've even made mistakes here in terms of squaring things. So you've got to make sure that you square the R. You square the distance. We'll see what that means. But guys, it's not directly proportional. That's not true. It's inversely proportional. Now, another way of saying inversely proportional to the square of the distances is to saying it's directly proportional to 1 over R squared. So that's a really important idea that you've got to get clear. That when we say something is inversely proportional also means directly proportional to 1 over. Directly to 1 over. So if it's inversely proportional, so F is inversely proportional to R squared, then it's directly proportional, then F is directly proportional to 1 over R squared. Please get that right. So when we go back and look at Newton's second law, we would say the acceleration is inversely proportional to mass. We can say A, the proportional sign, this sign, which is saying proportionality, there, as the one goes up, the other goes up. Here we're saying as the one goes up, the other goes down by the same proportion, but the same proportion squared. So it's not, that's why this inverse proportionality is sometimes difficult. And we're going to spend a little bit of time talking about that in some of the problems. Now, you're going to say to me, but guys, I don't want to deal with these proportional signs all over the place. I want to have an equal sign. And so in physics, when we have proportional signs, we can change them to equal signs if we introduce a constant. So we can now say the formula looks like this. Here's the constant, which has been found through measurement, G, m1, m2 over r squared. And that's very important. It's on the data sheet, but you need to know it, and you need to know how to apply it. There's one last thing, which again we'll come to in the questions. When we're dealing with Newton's law of universal gravitation, there's one other law that we need to take note of, and that is Newton's third law. And I'm just going to leave it there and say, you need to revise this. I'm not going to explain it. I'll explain it when we come to a problem. Megan?
You ready for a break?
I think let's have a break.
So quick and so thoroughly. But anyway, guys, don't go anywhere. Maybe just grab a little glass of water, but really, you don't want to miss out on this. We'll see you after the ad break. Welcome back, grade 11. So as we said, John was speaking about we're doing Newton's law or universal law, am I right, of gravitational acceleration.
No, not acceleration. Newton's
Law
of acceleration. Universal law of gravitation of
acceleration.
Ah, you've got me saying it. Okay, we're doing Newton's law. Let's move on.
That's much better. Okay, we're doing that. And please, guys, get entering in the Test Yourself competition. We did it in the beginning, and maybe you could be the winner of awesome Vodacom prizes. So get entering, and let's get learning more together.
Excellent. The questions are on the Facebook page. Make sure you get them. So let's go to the improve your skills questions now. These are in the notes. These are some typical exam type of questions. So I hope you got them, got your notes. Get the notes as soon as you can. Download them from the website. Do them before the show. Get going. Get some work done. Right, let's have a look at what it says. It says to us some important information. It says the radius of the Earth is 6,4 times 10 to the 8 meters, and its mass is 6 times 10 to the 24 kilograms. Then it says use Newton's law of universal gravitation to calculate the acceleration of an object falling from the second floor of a building, and it tells us that we can ignore the effect of air resistance. So we can ignore the frictional effect. Right, guys. What have we been given? We've been given the mass of the Earth. The mass of the Earth we've been given as a big number, 6,4 times 10 to the 24. We've been given the radius of the Earth. So the radius of the Earth, we've been given that is 6,4 times 10. This one wasn't 6,4. This was just 6. Sorry, I made a little error there. So this one was 6,0. This is 6,4 times 10 to the 8 meters. And this was kilograms. Okay? And what we're asked to do is to find the acceleration of an object falling from the second floor of a building. Hey, this seems impossible. Because I don't know anything about the object. I just know that it's falling down towards the ground. It's second floor of a building, not very high. So we can ignore air friction. What am I going to do? And what it's asking me to do is to calculate the acceleration. Where am I going to get all this stuff? Well, relax. Don't panic. What we've got to do is let's write the formula out. So the first thing that I'm going to do is I've got that information. I'm going to say we know the force of attraction between the object is equal to G times the mass of the object times the mass of the Earth divided by the radius of the Earth squared. That's the equation. Now, what else do we know about the object? We know it experiences a force. What force does it experience? And here's the important thing, guys. We need to get this very clear. It experiences a force, a pull down of the force of gravity on it. As I'm standing here, the Earth is pulling me down. And what force is it exerting? It's exerting a force that we call, another way of saying it, it's the force is equal to the mass times the acceleration due to gravity. And this is sometimes even called my weight. So into this formula which you might have seen when we dealt with Newton's second law, we can now combine these two and we can say, hold on, we know that mass, that the force acting on the object is the mass times the acceleration to gravity. And that's what we wanted to find. We wanted to find the value of little g. And watch here. G m e over r squared of the Earth. And what do you notice? I hope you can see that the mass of the object cancels out. I can divide both sides by m and they cancel out. What is this telling me? And it's a very important thing you've got to know. That objects accelerate close to the Earth independently of their mass. So if we ignore friction, they have the same acceleration. The only thing that gravitational acceleration depends on is this constant, g, the mass of the Earth and the radius of the Earth. Okay, guys, that's the physics part. We've got to get that clear and you've got to know it. You've got to make sure that you understand that the attraction between an object and the Earth is known as its weight and as mg. We can then find out what g is by doing the substitution. And this is where it becomes easy. I've just got to go back and remember that value. Megan, can you take a note of this? 6,67 times 10 to the minus 11. 6,67 times 10 to the minus 11. We're going to need it for just now. 6,67 times 10 to the minus 11.
Yeah.
Okay, got that right. The mass of the Earth was 6,0 times 10 to the 24. So I'm going to put that in brackets. 6,0 times 10 to the 24. And then I'm going to take the radius of the Earth, which was 6,4 times 10 to the 8 meters, and I must square it. Now, please watch very carefully that you do square it. You must put it into the calculator. And with this particular equation, you need to be very careful of using your calculator correctly. So make sure you're familiar with scientific notation and exponents. So let's go to our calculator here. We're going to say 6. Let's just take that off for a minute because it's going to give us grief. We go 6,67 exponent negative 11. And we want to times that by 6. Check the reading. Times 10 to the 24. And that will give me my numerator divided by, now I'm going to be careful because I know that I've made the mistake before. 6,4 exponent 8, and I've put it in a bracket because I want to square that whole thing, and I'm going to then make sure that that's the denominator, and I'm not forgetting that that's squared. And I push equals, and look at the size of this force. If I go to my scientific notation, which I'm just going to do it to engineering, you can see that it is, divide this, just to take it out of engineering for a minute, or it's going the wrong way. It's getting too big. Let's go back. It's gone too much. So what I'm going to do is I'm going to say that this is 9,7. Let's just make sure that we can go back one step. I want to go back. and it's not letting me. Dear, 9,17, and I'll get the reading here. It's going to be 77, 2 decimal places, times 10. Now, let me try and work out what it's given me, because I've made a really silly mistake there. I thought I was getting to the scientific notation, and I'm not. So if I do 12 places, 1, 2, 3, 4, 5, 6, 7, 8, 9, then that's going to be times 10 to the minus 2, I think. Okay, so we'll check it in the break. It's either times 10 to the minus 2 or times 10 to the minus 3. I'm not exactly sure why it's come out like that, because it should have come to a closer number that we're more familiar with. Because if you look at 9,7, that should really be the acceleration due to gravity. Maybe there's a slip, there's a factor of 10. I'll look at the question, but I hope you can see that that is the way to do it. This, of course, needs to have units, meters per second, and we'd get that as an answer. Okay, let's move on to the second question. We're going to use the same sort of idea, and let's see how we manage. So, calculate the magnitude of the force between a person with a mass of 100 kilograms and a person with a mass of 75 kilograms if they are 0,5 meters apart. Now, I know this is corny, but you probably hear it as whenever you doing this section, somebody will come up to you and say, did you know that I feel a force of attraction towards you? And it's nothing to do with your sparkling personality, it's just to do with your mass. We'll apply exactly the same formula. We're going to say, what's the force of attraction when we have G, M1, M2 over R squared? And guys, I'm not even going to go too far with this. I'm going to substitute the values in 6,67 times 10 to the minus 11. Mass of the one person was 100 kilograms. There must be SI units. And the other was 75 kilograms. And now we must make sure that we take 0,5 and we square it. 0,5, not 0,8. 0,5, and we must square it. So let's do that. Let's see if our calculator will behave, and we'll check it out in a minute. 6,67 exponent minus 11 times 100 kilograms. Make sure it does do what I say, times 75. Now, divided by 0,5 squared. Okay? That gives me an answer, and again, it's got 0,00, and I don't like those answers. So, I'm going to count the number of decimal places. 1, 1, 1, 2, 3, 4, 5, 6, 7. And that's, sorry, let me do it again. 1, 2, 3, 4, 5, 6. If I multiply this by 10 to the 6, then I'll get the answer of 2,0 times 10 to the minus 6
For
newtons.
those who don't know how to do scientific notation, is it just moving the comma?
Correct. So let's just check that out. And what I'm going to do is I'm going to multiply the answer by 10 to the 6. So I'm going to say multiply by 1 exponent 6. And let's see what we get as an answer. And there you go. So I've checked it.
Yes.
Okay? Because I've said it was 2 times 10 to the minus 6. If I divided by 10 to the minus 6, I would get 10 to the negative 6.
Yeah. Just
Okay?
for those who don't know.
So you've got the answer. You know that it's right. If your calculator, make sure your calculator is set up in scientific notation. Read the instruction manual to get that. So guys, in this section, you can see this question, really just plug and play. You're just putting it in. The big thing that I want to make sure of, and to say to you again, you've got to square. You've got to make sure that you square that distance. Recognize that this is a very, very small force. You know, it's 1/millionth of a Newton. It's not going to be, or 2 millionths of a Newton. Not very big at all. Okay, let's go to the next one, which requires a little bit more thinking, and we're going to have to play with it a little bit and understand the physics. So let's go to that, and let's see exactly where we are. So it tells us now the force between a man with a mass of 100 kilograms and the Earth is 9,800 newtons. If the mass of the Earth is taken as 6 times 10 to the 24, determine the radius of the Earth in kilometers. Now we're going to check if our answer that we used, the data that we used earlier, is actually accurate. So let's do it. We're going to use exactly the same formula. F is equal to G, M1 for the man, ME for the Earth, divided by R squared. But now, in this case, what are we asking? We're asking for R squared. Don't be tempted to change the formula. You must substitute in first. So we're going to substitute in for all the things that we're given. We're told that the force between the Earth and the man is 9,800. So we're going to put the 9,800 there. We're going to put the 6,67 times 10 to the minus 11 over there. Put it in brackets so we don't forget it. We've got the mass of the man. He's 100 kilograms. And we've got the mass of the Earth is 6,0 times 10 to the 24 kilograms. We don't know what R squared is. So that's what we've got to find. How are we going to do it? Multiply both sides by R squared, and we'll get the following. We'll get R squared, and then divide both sides by 9,800, and 6,67 times 10 to the minus 11 times 100 times 6,0 times 10 to the 24. And there you go. It's a simple matter of putting this into the calculator. Will we have the right answer then? Not quite. What have we got to do? We've got to remember that this is R squared. If I want to get R, what am I going to do? I'm going to take the square root of both sides, and I'm going to say it's the square root of this, 6,67 times 10 to the minus 11, okay, times 100, times 6,0 times 10 to the 24, and that's all in the square root, and then underline it by recognizing that this is the force, which is 990. Guys, I'm not going to do the calculation of that. Think you can manage on the calculator. This is not about calculation. I want you to see the different types of questions they can ask. Let's do one more, because this one gives us a little bit more thinking to do in terms of the actual law. It says, an object has a mass of 48 kilograms. What gravitational force will this object experience if it is released from a height equal to twice the radius above the Earth? And then they give you the data. So, this is a question that came to us on the help desk. Came the other week, and I want you to think about it very carefully, because the easiest way to do this is to draw a diagram. And we say that the object is above the Earth's surface, and it's a distance of twice the radius. So there's one radius, there's another radius, and there's the third radius from the center of the Earth. So the distance that the object is from the center of the Earth is 3r. And that's the critical point that you've got to make. We're told that it has a mass of 48 kilograms. We're told all the rest. And what we're having to do is to work out what gravitational acceleration will it experience. We don't even need to use its mass. We can simply say G is equal to big G, the mass of the Earth, over the radius of the Earth squared. And there we go. We've got the distance, and we've got the thing to substitute Last thing that I'm just going to do is I'm going to put the values in so you can see that we've got them. 6,67 times 10 to the minus 11 times the mass of the Earth, and I'm going to squash here, 6,0 times 10 to the 27. I think it was 24, wasn't it? Let's just check it. 24 kilograms. 24, there we go. And I'll move it now. And then the radius is 6,4 times 10 to the 8. And I'm just, this is jumping, and I don't know why. 6,4 times 10 to the 8. Don't forget to square. And again, I hope I can leave that for you to solve. But hold on, I've made a mistake. It must be 3 times that, because it's 3 times the radius. So don't forget, don't be in a rush like I was, because I can see time's running out. Make sure that you've got 3 times the radius. Why is it 3? Because it's 2 above the surface and 1 below to the center. Very, very important. Megan?
Okay, John, guys, it's time for an ad break. Quickly go get a glass of water, jump up and down, but don't leave your screens when we come right back from this ad break. See you then. Welcome back, Mindsetters. Hope you had a good break, but you guys are ready to learn. Get that pen, get that pad out, because we have to go through the challenge question. So, John, please enlighten our Mindsetters on what they actually had to answer.
Excellent. Guys, I hope you're with me. I know that the calculator made a few mistakes. Let's not worry about those. You've got lots of time to practice working on the calculator. I'm not going to go over those just yet. I'll post the answers at the end of this session on the Facebook page. So make sure you practice correctly. There were some people that said, why did you square? Why do you should have squared outside the brackets, inside the brackets. I probably did make a little mistake. But you're rushed up here, and it's not always that easy. Okay, so please be careful when you're using the calculator. Don't get flustered. Take your time carefully, and you'll be fine. Now, let's look at the challenge question. The physics of the challenge question is really important. And that's what I want to get to you this afternoon, is to deal this evening. Is to make sure that we're dealing with the ideas of Newton's universal law of gravitation. So here's the question. It says, a falling object falls to the earth. So there's obviously an attraction. The force of attraction between two objects, Newton said, is the force of gravitational attraction. That force is equal to G m1 big M over r squared. We sometimes also say that that force is equal to the weight. It's the mass times the acceleration due to gravity. Now, what you should notice is it's saying to us that the force exerted by the earth on the object, and it falls towards the earth, and that's the important thing, it falls towards the earth, because the force exerted by the earth on the object is greater than the force exerted by the object. Is this statement true or false? Now, we've set it up, we've got these two objects, the earth is one object and the other object is the other. And we're saying, why does the object fall to the earth? It's kind of like strange. Why is it the object that's falling to the earth, and why don't they move towards each other? If there is a mutual attraction between them, and that's the important thing, there is a mutual attraction, why does the one object accelerate towards the other, and it doesn't look like the other object's moving? The earth doesn't look like it's moving. I mean, if I stand on the top of a tall building and I jump, the earth doesn't move towards me, or does it? Well, that's the question. And so the answer is, and they're suggesting the reason the object falls towards the earth is that there's a bigger force. The object the earth is pulling downwards stronger than the object is pulling upwards on the earth. And that is wrong. The answer here is definitely false. And I've run out of space to write this. So I'm just going to write it over there, down at the bottom. And the reason that we say it's false is very important that you can explain, because it wasn't just say false and leave it like that. What we've got to do is we've got to be able to explain it. And here's the explanation. When we have when we have a force exerted on objects, and I'm going to just select my eraser because I want to take this part away and I want to draw a diagram. So let's get the diagram and let's go carefully. We're going to say they're the two objects. This is object A and this is the Earth. And I should make the Earth a lot bigger because it has a bigger mass. Okay? And what we're going to say is we recognize that the Earth exerts a force on object A. Correct. And we recognize that object A exerts a force on the Earth. And what do we know about those two forces? We know that they are equal in magnitude, but opposite in direction. And the reason for that is Newton's which law? Third law. Body A exerts a force on body B, then body B will exert a force on body A that is the same magnitude. They'll be equal in magnitude, but opposite in direction. And this universal law of gravitation is an ideal opportunity to explore that law and to revise it. You must be able to recognize that the force on body A, this is the force of the Earth on A, and this is the force of A on the Earth. And they're equal. But now why does the one accelerate towards the other? That's the interesting question. Now guys, in this system, we're not talking about any other forces. We're ignoring any other forces. We're saying that this is the only force. So this is a net force. What do we know about F net? We know F net is equal to the mass times the acceleration. So if the mass of the Earth is very big, and it is compared to any object, it's huge, okay? Then to get that force, it's going to be a little acceleration. Whereas on this object, which has a small mass, the acceleration has got to be much bigger. And so that's why the object falls towards the Earth, because we're also standing on the Earth and we're watching. The inertia of the Earth, because it has such a huge mass, isn't going to suddenly move upwards. It's not going to be disturbed because there are all sorts of other forces acting on universal forces of gravitational pull. The pull of the sun, which has a massive mass, the pull of the moon, the pull of the stars. They're all acting on the Earth. And my little jumping down on a building is not going to disturb the Earth. If we cancel all those forces out, it's not going to have an effect on the Earth actually moving towards me. But I'm going to, if I'm falling from a building or from an aeroplane with a parachute, I'm going to feel the acceleration because my mass is so much smaller than the mass of the Earth. Okay, so that looks like the challenge question done. We definitely know that it's a false answer, and we've explained why in fact the object is falling, because the mass of the Earth is so big, its acceleration is very, very small. The mass of the object that is falling is actually small, so its acceleration is quite substantial. And remember, on the Earth, in relation to objects falling, that acceleration is going to be constant up to a point. Obviously, the further and further away you get from the surface of the Earth, the less that acceleration is going to be. And so we've got to remember that as well, because it's directly proportional to 1 over r squared. Okay.
Ready for
Megan,
some questions,
we're ready
guys?
for some questions. Let me just get a
Let's go.
blank sheet,
Okay.
because that
Much
page
easier.
wasn't behaving very nicely.
Bad
And,
page.
yeah, it was behaving badly. And even this one. But we've got some space. So let's go.
You ready? Okay. So Libia Jamor says, what is the difference between a lowercase g
Okay.
and big G, if that
Okay.
makes sense?
So this G
And
and that G.
capital G.
Very
yes.
good. Guys, It's a very good an important question. This one is equal to, on Earth, 9,8 meters per second per second. And this is what we call the acceleration, what we were talking about there, the acceleration due to gravity, due to the Earth's gravitational field, really, but we say it's due to gravity. So around the Earth, any object will have an acceleration towards the Earth. It's a downward acceleration at that particular acceleration. Okay, so it's got units of meters per second squared, so meters per second, and we recognize that that's on the Earth. Only when we use the little g, we are referring to Earth. On other planets, that pull on an object would be different, depending on the mass of the object and the radius of the planet or satellite. So on the moon, for example,
Yeah, we're
going to come to that. Yeah. So you're going to get a different acceleration. We'll come to that in a second. Let's just answer this question. What about this value here? This g, this is a constant. It's called the universal gravitational constant. And what we're saying here, the value 6,67 times 10, or let's just make that a proper times. I think that was the one. No, and it's gone again, sorry. Times 10 to the minus 11. And we can work out what the units are, even though they're in the notes. It will be newtons. And then we're going to, sorry, is it newtons? Let's just rewrite the equation. F is equal to G m1 m2 over r squared. And if we get G on its own, then we're going to get G is equal to F r squared over m1 m2. Now the units of force is newtons. R squared will be meters squared, and then we're going to go per kilogram to the minus 2. So those are the units, and we've cancelled those out and made sure that that's everything. This is a mathematical term. It's got nothing to do, it's from an experiment. It's the value that gives us that straight line. So if we were to plot these points here, we plot those quantities, we would get a straight line with that gradient. So that's how they work it out. It comes from the experiment. It's an accepted constant. Makes the two systems not be a proportionality sign. We can replace the proportionality sign with an equal sign. When we did Newton's second law, you define the Newton, the proportionality constant is 1, and that's why we don't have one. But in many other equations, we have a proportionality constant. Okay.
Ready?
Now,
One more?
one more? Yeah, let's go for
can
it.
we do the moon one?
Yeah, let's go for the moon.
Please, okay. Mozobazi Soli says, please explain the weight of an object on the Earth and the weight of the object compared to being on the moon.
Okay, so on the Earth, the weight is mg. The mass doesn't change. The mass on the weight on the moon is also equal to mg, but mg here must be the g of the moon. And what we know is the masses will be the same. That's the important thing. But the value of this gravitational constant is 1/6 of the g on the Earth. Okay? In other words, you have to divide that 9,8 times 10, 9,8 by 6. And it comes out to 1,6 something. That will give you the difference between the force on the moon and the force of an object on Earth. Megan,
You ready to go? Okay, mindsetters. I just want to say Martique has been asking me to send a shout out to Lindre, Nikki, Kim, and another mindsetter said to Buchle. Thank you for tuning in. Please don't go away if you're a matric, because we are up next with grade 12 physical sciences. But thank you for this. It was really awesome to be back. I hope you learned a lot about Newton's laws, because I did. So have a good evening. See you guys, same time, same place next week. Cheers, guys.